In this video, we're going to look at wave-particle duality and the photoelectric effect. All right, wave-particle duality. So far this year, we've treated waves like waves and particles like particles. But here's the thing. Scientists have found that particles behave like waves, and waves behave like particles. So electrons have been observed to behave as if they were waves. And photons, which are, those little light energy packets, have been seen to act like particles. This phenomena is known as wave-particle duality. All right, well, let's first look at an electron. This equation is known as the de Broglie, yes, yay, we love de Broglie, wavelength. And basically, it's taken the electron that acts as a wave and says, okay, I want to know the wavelength of the electron. Okay, so what is that electron's wavelength? Well, that electron's wavelength depends on its momentum, lowercase p. And of course, momentum is mass times velocity. P equals mv, if you remember from way back. Okay, so basically the wavelength of an electron depends on its velocity. It also depends on two constants. H. We're going to be seeing a lot of H. H is known as Planck's constant and is 6.63 times 10 to the negative 34 joules times seconds. So that's its unit. You can find it on the first page of your reference table. The other constant in this one is, because we're looking at an electron, the mass is the mass of an electron, which is also in your reference table, as 9.11 times 10 to the negative 31st. Okay, so if I want to find the wavelength of the electron, all I need to do is know how fast it's going. All right, so that's a particle acting like a wave. Now, photons. Photons have energy. These are waves, light waves, electromagnetic waves. They have energy. The amount of energy is dependent on its frequency. Okay, so we have the equation E equals HF. The energy is Planck's constant times its frequency. Now, E also equals hc over lambda. So the energy is equal to Planck's constant times the speed of light times the wavelength. Now, how did I get from here to here? Well, that's fairly easy. V equals lambda F. We know that from before. If we're talking about photons, then they have a velocity of c. C is the constant speed of light, so its velocity is c, lambda F, which means F is equal to c divided by lambda. So h times c, or h times f, or h times c over lambda. C is 3 times 10 to the 8th, and lambda is your wavelength. So the amount of energy is directly related to the frequency and inversely related to the wavelength. All right, so previous slide, E equals hc over lambda. All right, we had that equation. Now, on the slide before, we had wavelength is h divided by p, momentum. If I was to combine these two together and basically plug this in here, I would get E equals hc, and then I would plug in for lambda, and that would become h over p. My h's would cancel, and the energy is equal to c times p. Or rewritten is this equation. Now, why is that important? Well, that's important because that's telling us that photons, light, has momentum. Despite having zero mass, it has momentum. And we know momentum is mass times velocity in classical mechanics. And this is where modern kind of goes, woo, woo, and has a little bit of fun. Okay, so we can say, well, that's just a bunch of equations. I can say whatever I want with equations. But this has actually worked out, and we've seen it in real life. So let's do an example. An electron at rest absorbs 4.1 times 10 to the negative 19. So that should say 4.1 times 10 to the negative 19 joules of energy from a photon. What is the velocity of the electron? All right, so this is one that it's kind of a flashback to the equation, to an old equation. Remember, if we're solving for velocity and we have energy, let's think we have energy, velocity, energy, velocity. What connects them? Kinetic energy. Kinetic energy is 1/2 mv squared. So the kinetic energy, which in this case is 4.1 times 10 to the negative 19th, is equal to 1/2 the mass of an electron, which is 9.11 times 10 to the negative 31st, times v squared. And we solve for v. And we get, see, 4.1 times 10 to the negative 19 times by 2, or divide by 1/2, divide by 9.11 times 10 to the negative 31st. And I get v squared is equal to 9.001 times 10 to the 11th. So I got to take the square root and get 9.49 times 10 to the 5th equals the velocity of the electron. All right, so if I know the velocity, my next step is going to be the wavelength. Wavelength is h divided by p. It's also equal to h divided by mass times velocity. So my wavelength is equal to Planck's constant, 6.63, times 10 to the negative 34th, divided by the mass of an electron, 9.11, times 10 to the negative 31st, times its velocity, which was 9.49, times 10 to the 5th. So we plug it in. And we get a wavelength is equal to 7.67 times 10 to the negative 10th. And if I want my momentum for the third part, the momentum of the photon. All right, so momentum of the photon, not momentum of the electron. If we were using momentum of the electron, we would just do mass times velocity and we'd be good. We want momentum of the photon. So momentum of the photon comes from the amount of energy it has. Okay, so P equals E over C. Okay, because it's massless, we can't use mass times velocity. So the momentum, or the photon had momentum, or energy, excuse me, of 4.1 times 10 to the negative 19, divided by C, which was 3 times 10 to the 8th. All right, so as you can see, the math here is not too bad. You just have to know when to use what. And you get 1.367 times 10 to the negative 27. Okay, so your equations are up top. We have this one we use, this one, and this one. And the math isn't bad, just figure out which one you need to use. So, I've been telling you photons have momentum. And I told you we also had proof. We do. If you've ever put metal in the microwave, you have absolute proof that photons have momentum. Because what happens when you put metal in the microwave and you hit start and you run it, it sends these waves out. Lots and lots of waves, microwave, into the metal. And metal has, that sea of electrons, has lots of electrons. So what happens is those waves start hitting those electrons, and the electrons start bouncing off and sparking and going nuts and going crazy. And yeah, photoelectric effect. Okay? So that's how we see it in the microwave. You see it at a less spectacular level when you deal with solar power. Solar power has light shining down on a panel of some sort of material, and that light hits the electrons and causes them to bounce off and basically creates an electric current. You knock the electrons off, they get a current going through, okay, and it's kind of a consistent process because the electrons get bounced off, they leave, right, and they get replenished. So photoelectric effect is actually solar electricity. And solar electricity is one of the few that's very different. Most electricity is used like what we looked at with magnetism, with the rotating magnet, but not this one. All right, so properties of photoelectric effect. You maybe ask questions along the lines of how does this affect it, or which is true. For light, if it has a greater frequency, it's going to have more energy. Okay, which means that the electrons are going to escape with more energy. So if I'm kicking an electron off of it, it's kind of like giving it a little nudge, and then more energy would be like push. Okay, but that's not necessarily going to affect, let's say, how bright the light is that comes off of it or light from it. The brightness means more photons. So not photons having more energy, but a greater number of them. So greater brightness means more electrons will be escaping. So you have a larger current. So, how fast something is moving means more energy. How many means more bright. All right, photoelectric effect. Every type of light has a different amount of energy. And we have this beautiful thing that came off of Wikipedia. Thank you. This one's actually very nice, and I really enjoy this one. Okay. Basically, each light has a different frequency. E equals HF. Right? Your frequency versus your wavelength, or E equals hc over lambda. So as your wavelength goes up, your energy goes down. Right? So as my wavelength gets bigger, energy goes down. As my frequency gets bigger, my energy goes up. Okay? So if we look at the visible light spectrum, red has less energy than green or blue. Blue has the most. Okay? Ultraviolet light has more energy than infrared or microwaves. Okay? So, photoelectric effect. In order to knock those electrons free, it takes a certain amount of energy. So, if I shined red light onto a surface, maybe nothing would happen. Red light may not have enough energy to kick the electrons loose. I could keep it going, keep shining and shining and shining, and nothing would happen. Doesn't matter how bright the light is, okay, because bright is number of photons, or number of electrons. Doesn't matter how bright it is. It just matters how much energy. So green might kick one loose. But if you look at the difference in arrow sizes, blue kicks it loose with a faster velocity. All right, so that minimum amount of energy needed is known as your cutoff frequency. Sometimes it uses the word threshold frequency. Okay. This is also known in terms of energy as the work function. So the frequency, the cutoff frequency, is basically that minimum frequency needed to knock the electron loose. And the energy associated with that frequency, because E equals HF, the energy associated with that frequency is known as the work function. So basically that cutoff frequency times Planck's constant is your work function. So let's look at the equations. Okay, I was just talking about work function, so I'm going to drop down here first. Work function is represented by the symbol phi, and that's just a line with a circle. Okay, and that is H times your cutoff frequency, which is F naught. Okay, so I'm shining light of a certain frequency on the surface. That is H times F. F is the frequency of the incoming photon. Okay, so that's the energy incoming. Now, H times F naught is the energy needed to kick it loose. So, energy needed. Now, if you have more energy coming in than you needed, you're not only going to kick it loose, you're going to kick it loose and send it on its way. And that extra energy becomes kinetic. Okay? Now, if you want to know, is the electron going to escape or not? If you plug it into that equation and your kinetic energy is less than 0, it's not going to escape, which basically means it needs more energy than it's got. And if it's positive, then it's going to escape. Now, how do we determine those cutoff frequencies? Those cutoff frequencies are determined by the stopping potential. So what scientists did is they basically set up a cathode and an anode, so a positive and a negative. The anode is the negative. And they shined a light of a known frequency, and they kicked an electron loose. And they basically found out what this potential difference needs to be in order to stop the electron. By doing that, they were able to basically find out how much energy was left over. Okay, stopping potential gives you that leftover energy, also known as the kinetic energy. So if you know its stopping potential, then you know the kinetic energy. And once you know the kinetic energy, you can find the cutoff frequency or the work function. All right, Q is the charge of an electron, 1.6 times 10 to the negative 19th. Okay, V is volts. That should be coulombs. Okay, and V naught is your stopping potential. So once that electron escapes, the stopping potential is basically the amount of potential you need to make it stop. Now let's see how that would be useful. I'm going to pick those two equations, and I'm also going to show you a graph. A graph is just another way to get the numbers. Rather than you writing out the numbers in the problem, I just put them in a graph. All right, so using the graph on the next slide, determine the cutoff frequency. The cutoff frequency is basically where the incoming light and the kinetic energy, okay, let's see, let me write it out here. Kinetic energy equals HF minus HF naught, right? So if I'm looking for this, then where my kinetic energy is 0, HF is going to equal HF naught. Okay, H's cancel. So right here, where kinetic energy is 0, this is my cutoff frequency. So 4.5 times 10 to the 14th. Okay, so that's my cutoff frequency. Check. Work function, phi, That is equal to H times F naught. So that's equal to 6.63 times 10 to the negative 34th times 4.5 times 10 to the 14th. And I get 2.9835 times 10 to the negative 19. All right, so I know my work function. I want to calculate the kinetic energy of an electron that has been ionized by a photon with a frequency of 10, and that should be to the 14th hertz. All right, so if I'm solving for kinetic energy, I can use this one or this one, but I don't know stopping potential, so not this one. All right, so we're going to use kinetic energy is equal to HF minus HF naught, also known as V, since we already solved for work function. So my kinetic energy is equal to H times my incoming energy, which in this case was 8.3 times 10 to the 14th, minus C, which I found there, and I end up with a kinetic energy of 2.5194 times 10 to the negative 19th. So I did 6.63 times 10 to the negative 34th. That's H times F, which was 8.3 times 10 to the 14th. And I subtracted that one we found before, which was 4.5. Oh, sorry, 2.9835. Okay, and I got this kinetic energy in joules. All right, check. And stopping potential. Well, I know kinetic energy is equal to QV naught. So I plug my kinetic energy in there. Equals 1.6 times 10 to the negative 19th. V naught. So divide that kinetic energy. And you got V naught is equal to 1.5746. See, not too bad. The hardest part was reading the graph, and now you know how to do that. All right, that's it for the lesson. Good luck on your homework.